Okay, let's unpack this. Today we're diving deep into an architecture that has, well, fundamentally reshaped AI and machine learning, the transformer. You've probably heard of models like BERT, GPT, DALI. They all pretty much stand on the shoulders of this one incredible idea.
Yeah, it's fascinating. What's really striking is how a single paper from 2017, the attention is all you need paper, didn't just propose a new model. It really ignited a revolution with a concept that was surprisingly simple yet incredibly powerful.
Exactly. So our mission today is to explore the genius behind that original transformer, really understand why it was such a game changer, and then we'll journey into this cutting-edge world of efficient transformers models designed to overcome its biggest challenge. We're pulling insights from that foundational paper and also two really comprehensive surveys, Efficient Transformers,
Yeah.
a survey, and a survey of transformers, both from 2022. So as we kick things off, what aspect of that original breakthrough really stands out to you first?
I think what stands out immediately is just the sheer audacity, really. The way the original paper just completely discarded the dominant approaches in sequence modeling at the time.
Right. Let's rewind to 2017 then. Before the transformer, the go-to models for handling sequences like sentences and machine translation, for instance, were mainly recurrent or convolutional neural networks, RNNs and CNNs. But they had some pretty inherent limitations, didn't they?
They absolutely did, yeah. Recurrent models, they process information sequentially, token by token, which means they can't really parallelize computation within a single training example. And that becomes a huge bottleneck, especially when you have longer sequences. And sure, attention mechanisms were already being used with RNNs to help model dependencies regardless of distance, but that core sequential constraint, it remained. Convolutional networks, on the other hand, they often struggled with long-range dependencies. They typically needed many, many layers to connect distant positions in a sequence.
Okay, here's where it gets really interesting then. The transformer proposed this radical shift, just ditching recurrence and convolutions entirely, relying solely on attention mechanisms, which, when you think about it for sequence processing, sounds almost counterintuitive, doesn't it?
It really does, and it raised this important question. How could a model effectively process sequences without that traditional sequential processing or, local convolutions? The answer lies in its innovative architecture and, critically, in its very unique attention mechanism.
So if it's all about attention, what does that mean for its actual structure? How do they build it?
Okay, so at its core, it's an encoder-decoder architecture. That part is similar to many sequence transduction models, but the real novelty is that it's built entirely with stacked self-attention and pointwise fully connected layers. That's the quote. Both the encoder and the decoder are composed of 6 identical layers in the original paper. Each encoder layer has 2 main sublayers, a multi-head self-attention mechanism, and then a position-wise fully connected feed-forward network. The decoder layers add a 3rd sublayer. This one performs multi-head attention over the output of the encoder stack. This allows every position in the decoder to attend over all positions in the input sequence. It mimics that typical encoder-decoder attention.
And these stacks, they use residual connections and layer normalization too, like we see in other deep nets.
Correct, yeah. They're used around each sublayer. Helps with training deep networks. And a really crucial detail for the decoder is that its self-attention is masked. This basically prevents positions from attending to subsequent positions, to tokens that come later in the sequence. And that ensures its autoregressive property for generation, meaning it generates tokens one by one, relying only on the ones it's generated so far.
Wow, that's a lot of intricate pieces working together. But let's talk about the real secret sauce you mentioned earlier, attention itself.
Indeed. The core of it is what they call scaled dot product attention. So it computes dot products of queries with all the keys. Then it scales them by dividing by the square root of the key dimension, that's the score to dt. After that, a softmax function is applied to get the attention weights. Now, this scaling factor, it's really crucial because for larger dimensions, those dot products can get quite large. And large values can push the softmax function into regions where it has extremely small gradients, which is, well, really problematic for learning. The scaling counteracts this effect. It's also much faster and more space efficient than older methods like additive attention, mainly because it can use highly optimized matrix multiplication code.
Okay, so that's the core attention, but then they introduce multi-head attention. What's the advantage there? Why not just one big attention?
Right. So instead of just one large attention function, the model projects the queries, keys, and values multiple times. The original paper used 8 parallel heads. Each head performs that scaled dot product attention in parallel, independently. The results from these separate heads are then concatenated together and projected back to the original dimension. And the idea here is that this allows the model to, and I quote, jointly attend to information from different representation subspaces at different positions. You can kind of think of it like giving the model multiple specialized lenses, right? Each looking for different kinds of relationships in the data, things a single attention head might just average out and miss.
Got it. You also mentioned these position-wise fully connected feed-forward networks, the FFNs. What role do they play if attention is doing all the heavy lifting of relating tokens?
That's a good question. These FFN networks are applied to each position separately and identically within both the encoder and decoder layers. Architecturally, they're pretty simple. Just two linear transformations with a row U activation in between. But while they seem simple, they turn out to be vital. Later research actually observed that just stacking self-attention modules can lead to something called a rank collapse problem, where the representations kind of lose their diversity. The FFNs are crucial for mitigating this. They allow the model to perform these important nonlinear transformations on the attention outputs. You can also think of them as two convolutions, essentially, with a kernel size of 1.
Okay, that makes sense. And since there's no recurrence, no step-by-step processing, how does the model actually know about the order of words? How does it understand position? That seems critical for language.
It is critical, yeah. The original transformer introduced positional encodings to handle this. They did this by adding sine and cosine functions of different frequencies directly to the input embeddings at the bottom of the encoder and decoder stacks. This cleverly injects information about the relative or absolute position of tokens into the model. The authors hypothesized this would allow the model to easily learn to attend by relative positions. And fascinatingly, they actually found that learned positional embeddings produced nearly identical results to their sinusoidal ones. But they chose the sinusoidal version because, as they put it, it may allow the model to extrapolate to sequence length longer than the ones encountered during training, which is a potential advantage.
Okay, so we have this attention-only architecture, positional encodings. Why did this approach work so astonishingly well? What were the big wins compared to RNNs and CNNs?
Well, it really boils down to a few key advantages. First, and maybe most importantly, a massive leap in computational efficiency. A self-attention layer connects all positions with a constant number of sequential operations, technically O1. You compare that to recurrent layers, which require ON sequential operations, where N is the sequence length. This means you get significantly more parallelization during training. You can process all tokens essentially at once, which dramatically speeds things up.
So it could process everything in parallel instead of that slow, one-by-one sequential bottleneck.
Precisely. That was huge. Second, it was much better at handling long-range dependencies. Self-attention offers a constant maximum path length, again O1, between any two positions in the sequence, no matter how far apart they are. Recurrent networks have an ON path length, and convolutional networks have something like O-locdel or O-unc, depending on the setup. Shorter paths just make learning those distant relationships, like a pronoun referring back to a noun many words earlier, much, much easier for the model. And finally, there was some evidence for improved interpretability. The authors observed that individual attention heads seemed to learn to perform different tasks, and many showed behavior related to the syntactic and semantic structure of sentences. It gave us a bit of a glimpse into how the model might be reasoning, which was exciting.
And the results, the actual performance numbers, they were truly state-of-the-art, weren't they? I remember seeing those BLEU scores causing quite a stir.
Absolutely groundbreaking.
Yeah.
Yeah. On the WMT 2014 English to German translation task, the big transformer model achieved an impressive 28.4 BLEU score. Now, BLEU is a standard metric for machine translation quality, and that score improved over the existing best results, including ensembles of models, by over 2 BLEU points, which is a massive jump in that field. For WMT 2014 English to French, it hit a new single-model state-of-the-art BLEU score of 41.8. And crucially, these superior results came with significantly lower training costs. The big model trained in just 3.5 days on 8 P100 GPUs. That was, quoting them, a small fraction of the training costs of the previous best models. Even their smaller base model surpassed all previously published models at a fraction of the cost. It also generalized well. They successfully applied it to English constituency parsing, outperforming strong baselines like the Berkeley parser, even with limited training data for that task. This really established the transformer as this formidable new force, proving its adaptability and efficiency way beyond those traditional recurrent or convolutional models.
That's just incredible. A real triumph of efficiency and performance right out of the gate.
Mm-hmm.
But the original transformer, despite this amazing success, quickly ran into a pretty significant hurdle, didn't it? Especially as people wanted to apply it to even longer sequences, things like full documents, high-resolution images, or maybe even videos. What was the core challenge it faced when trying to scale up?
Yeah, that's the well-known Achilles heel, really. It's the quadratic time and memory complexity of that self-attention mechanism, specifically computing the QKT attention matrix, that multiplication of your queries matrix with the transpose of your keys matrix. It consumes n squared time and memory, where n is the sequence length. And this just rapidly becomes prohibitive for very long inputs. Imagine doubling the length of your input sequence, maybe going from a sentence to a paragraph. The attention computation quadruples in cost. That's just not sustainable for really long sequences. And while the feed-forward layers are linear with respect to sequence length, which is better, they still contribute a non-trivial amount to the overall computational cost, especially in large models.
Okay, so this quadratic scaling, this n-squared problem, that's what spurred this dizzying number of X-former models we
Mhm.
started seeing everywhere. Names like reformer, linformer, performer, longformer, all trying to improve upon the original, right?
So when we talk about efficiency here, what exactly are we aiming for? What does efficiency mean in this context?
Right. Efficiency here really encompasses two main things. First is the model's memory footprint. This is especially critical on hardware accelerators like GPUs or TPUs, which often have limited onboard memory. That N2 memory usage is a killer there. Second is the computational cost, usually measured in FLOP's floating point operations. We want to reduce the number of calculations needed for both training the model and running inference with it. The sort of overarching goal behind all of this efficiency work is enabling transformers to finally handle these large inputs and long sequences effectively, making them practical for widespread adoption and all sorts of real-world applications that the original couldn't easily handle. It really sounds like an entire new subfield just popped up to tackle this one efficiency problem. It can feel a bit overwhelming trying to make sense of all these different X-formers.
Mhm.
How can we maybe categorize them or, break them down to understand the main approaches?
That's a good way to think about it. We can definitely characterize them by their core technical innovations and the main strategies they use to get around that quadratic bottleneck. One major, probably the biggest category is sparse attention. This is a really broad umbrella term, but the basic idea is to reduce computation by making that NXN attention matrix sparse. Instead of calculating attention scores for every single query key pair, you only calculate it for specific selected pairs.
Oh, okay. So essentially teaching the model or forcing the model to be more selective about where it actually pays attention, not looking at everything.
Precisely, yeah. And within sparse attention, you have different sub-strategies for how you achieve that sparsity. Some use fixed patterns. These methods predefine the structure of the attention, deciding beforehand which pairs will interact. For instance, blockwise or local attention divides the input into fixed blocks or windows, and attention is computed independently within each block. It dramatically reduces complexity, kind of like only letting words pay attention to others nearby. Examples include the memory compressed transformer and the image transformer. Then you have things like strided patterns or dilated patterns. These attend at fixed intervals, maybe every second token or every fourth token, which increases the model's receptive field without quadratically increasing computation. The sparse transformer and the longformer use variations of this. Longformer is a really well-known one. There's also global attention, where you introduce a few global nodes, maybe special tokens, or just important tokens from the input that can attend to everything, and everything can attend to them. This acts as a sort of information hub. Longformer uses this too, as do models like ETC and BigBird. Some even use random attention, like in BigBird, where each query just randomly samples a few keys to attend to, hoping to catch some non-local interactions that way. And often, models use compound sparse attention, combining several of these fixed patterns like local, dilated, and global to get the best of all worlds. The axial transformer is a neat example, especially for images, applying attention along one axis at a time.
Okay, so those are all predefined patterns. But surely there are models that are smarter, more dynamic about where they focus attention.
Yes, exactly. That leads us to learnable patterns, sometimes called content-based sparsity. Instead of fixed patterns, these models learn which tokens to attend to based on the actual input content itself. The reformer, for example, uses something called locality-sensitive hashing, or LSH. It's a clever technique to efficiently cluster similar queries and keys together, so tokens only need to attend to others within the same hashing bucket. It's a way to dynamically group relevant information. Another one, the routing transformer, uses online k-means clustering to group queries and keys, with queries only attending to keys in their assigned cluster.
That makes a lot of sense dynamically figuring out what's relevant. Okay, so beyond making attention sparse, what's another major strategy people have tried?
Another important direction is using neural memory or global memory. These methods introduce a learnable side memory module. It often consists of a small number of inducing points or global tokens that can effectively summarize or access multiple input tokens at once. This memory acts as a kind of bottleneck, compressing the sequence information before the full attention calculation. The set transformer is a key early example here. It reduces complexity from quadratic ON2 down to ONM, where M is the number of memory points, which is usually much, much smaller than N.
Right, so instead of every token directly attending to every other token, they funnel information through these smaller set of memory points first.
Exactly, that's the core idea. Then another popular approach is low-rank methods. These methods try to approximate that big problematic NXN attention matrix with a matrix that has a lower rank, meaning it can be represented more compactly. The linformer, for instance, achieves this by projecting the key and value matrices down to a much smaller, fixed-length K before computing the attention scores. This cleverly reduces the complexity down to linear, ON. The Nystrom former is another example, using similar low-rank approximation ideas.
Okay, so we've got being selective, sparse, using memory bottlenecks for approximating the attention matrix, low rank. What else is in the toolbox?
Well, a really elegant mathematical approach is using kernels, often referred to as linearized attention. This approach reformulates the entire attention mechanism using kernel functions from mathematics. The clever trick here is that it allows you to change the order of operations so you can compute the attention output without ever explicitly forming that huge NXN attention matrix. This directly leads to linear complexity, ON or OT, with respect to sequence length. Performers using random feature approximations of kernels and linear transformers are probably the most notable examples here.
Wow, that sounds like a really fundamental rethink of the calculation itself.
Yeah.
Very cool. What about bringing back some ideas from the models the transformer originally replaced, like recurrence?
You're absolutely right. It's kind of ironic, but recurrence has made a comeback, often used in a divide and conquer strategy for very long sequences. These models typically process long sequences by breaking them into smaller segments. They process each segment with a transformer, but use a recurrent mechanism to connect information between segments, often by maintaining a cache or memory of hidden states from previous segments. Transformer XL was a pioneer here, introducing this segment-level recurrence with state reuse. The compressive transformer took this idea even further, adding multiple levels of memory to store compressed representations of even older activations, allowing context to potentially span much longer distances. It's about being smarter with how you manage context over time, essentially.
Interesting. And what about just making the sequence shorter somehow, reducing the overall size of the problem?
That's the core idea behind downsampling methods. These models work by reducing the sequence resolution, or length, at various points in the network to lower the computational cost. The funnel transformer, for instance, uses this neat funnel-like encoder that gradually reduces the sequence length through pooling, processes the shorter sequence, and then gradually reconstructs it. The perceiver and perceiver I/O models also fall broadly into this category, using cross-attention mechanisms to distill large inputs down to a smaller latent array. The Swin transformer in Vision also uses shifting windows and merging layers to create hierarchical representations, effectively downsampling.
Okay, and one last major category you mentioned, which sounded intriguing, something about only using resources when needed.
Yes, that covers sparse models and conditional computation. Now, while not always solely focused on the attention mechanism's complexity, these models improve overall efficiency by sparsely activating only subsets of the model's parameters for any given input. The most common approach here is using mixture of experts, or MOE, architectures. The switch transformer is a great example. It routes each input token to only one specialized expert subnetwork, usually an FFN layer, out of many possible experts. This allows you to dramatically increase the total number of parameters in the model, making it potentially much more capable while keeping the actual computational cost per input token constant, because only one small part of the model is activated. G-Shard and STMOE are other examples in this vein. It's about scaling up capacity efficiently.
It's just incredible the sheer amount of creativity that went into tackling that n-squared problem. Sparse, memory, low rank, kernels, recurrence, downsampling, conditional compute. Wow. But beyond these major efficiency categories aimed squarely at the attention bottleneck,
Yeah.
it seems like there's been a lot of other innovation happening at the architectural level, just refining the transformer itself, right?
Oh, absolutely. The community didn't just focus on the N2 problem. People have tweaked almost every part of the original design. Take position representations, for example. We talked about the original sinusoidal positional encodings, but many models explored learned positional embeddings instead. Or, perhaps more significantly, relative position representations, which became very popular. These focus on encoding the relative distance or relationship between tokens rather than their absolute position in the sequence. Models like T5, Transformer XL, and DiBerta incorporate different forms of relative position information directly into the attention mechanism. There are even hybrid approaches trying to capture both absolute and relative information. It's a really active area.
And what about layer normalization? That seems like such a minor detail, maybe? But I know from experience that normalization can be absolutely critical for getting large models to train properly.
You're spot on. It is critical. And the placement of the layer norm layer has been a surprisingly big area of research and debate. The original transformer used what's called post-LN, where the normalization happens after the residual connection adds the input to the sublayer's output. This sometimes leads to slightly better final performance, but it can make training unstable, especially for very deep models. The gradients can explode or vanish. So many later implementations, including BERT and GPT models, switch to pre-LN, where normalization happens inside the residual branch, before the attention or FFN layer. This generally leads to much more stable training, allowing for deeper models and higher learning rates. There are even efforts towards normalization-free transformers, like ReZero, which uses a simple learnable scalar gate on the residual connection, initialized to 0, to achieve stable training and faster convergence without layer norm at all. These seemingly small architectural tweaks can make a massive difference in practice.
So even the simple feed-forward layers, the FFNs, haven't escaped modification.
Not at all. Even the position-wise FFN modifications have seen plenty of action. Beyond the original ReLU activation function, models now commonly use others like Swish, or especially GELU, which is standard in BERT and many subsequent models. GLU variants have also shown promise. Some work has even explored greatly enlarging the capacity of these FFN layers, sometimes replacing them with more complex structures like product key memory layers, or, as we just discussed, using those mixture of experts approaches within the FFN block itself. And interestingly, almost counterintuitively, some studies have suggested that FFN layers can sometimes even be dropped completely from certain parts of the model, particularly later decoder layers, without a significant loss in performance on some tasks, which is quite surprising.
That is surprising. What about trying to strengthen the connections between different layers or blocks in the transformer stack?
That's another interesting area. Strengthening cross-block connectivity. Instead of just having the output of block L feed into block L plus 1, some models have explored ways to create shorter paths through the network. For example, transparent attention allows the decoder's cross-attention mechanism, where it attends to the encoder output, to use a weighted sum of representations from all of the encoder layers, not just the final one. This effectively shortens the path for error signals during training, potentially helping the model learn dependencies between the input and output more efficiently.
Hmm. And then there's this idea of adaptive computation time, which sounds really clever, like the model being smart about how much work it actually needs to do for a given input.
It's a fascinating concept, yeah. ACT allows the model to dynamically adjust the amount of computation it performs based on the complexity of the input token or sequence. For hard examples, maybe ambiguous words or complex sentences, it might apply more computational steps, perhaps by iterating a layer multiple times or passing through more layers. While for easy examples, it could potentially exit early, saving significant resources. The universal transformer used a dynamic halting mechanism based on a learned sigmoidal probability. Other models like DBERT implement early exit mechanisms where predictions are made at intermediate layers, and if the model is confident enough, say based on the entropy of its output probability distribution, it exits without computing the remaining layers. It's all about intelligent resource allocation on a per-input basis.
Very efficient. And finally, you mentioned handling truly massive inputs like entire books or maybe long videos requires a different structural approach.
That's where hierarchical transformers often come in. These models are designed to handle inputs that have a natural hierarchical structure or are simply too long for standard models, even with efficiency tricks. They typically work by decomposing the input into finer granularities. For instance, you might process individual sentences or patches with one transformer, then aggregate those representations, and then process the aggregated sequence, representing paragraphs or larger image regions, with another higher level transformer. This helps manage the computational cost for long inputs with limited resources, and it can also create richer, multi-level representations that are beneficial for tasks like document summarization, like Hybert, or complex computer vision tasks where you need to integrate local details with global context.
Okay, it's crystal clear that the architectural innovations, both for efficiency and just general refinement, are truly astounding. It seems the transformer wasn't just a model, it was a platform for continuous invention. But all this flexibility and power, especially the ability to handle parallel computation, it seems like it unlocked an entirely new paradigm for actually developing models, something maybe even bigger than just the architecture itself. The era of large-scale pre-training, right?
Absolutely. That's perhaps one of the most profound impacts. Because the basic transformer architecture makes few assumptions on the structural information of data, as one of the surveys puts it. It can be quite data hungry and prone to overfitting on smaller, task-specific data sets. This is where pre-training became absolutely critical. By training these massive transformer models on enormous, unlabeled data sets, like vast amounts of text from the internet or huge image collections, the models learn powerful universal representations. They learn about grammar, facts about the world, common visual patterns, all without explicit labels. Then you can take this pre-trained model and fine-tune it on a much smaller labeled dataset for your specific task, like sentiment analysis or object detection. And it performs vastly better than training from scratch. This pre-train and fine-tune paradigm fundamentally changed how most state-of-the-art AI models are built today.
And we generally see this manifest in three main flavors of pre-trained models, right? Depending on which parts of the transformer they use.
Yes, broadly speaking. First, you have encoder-only models, like the famous BERT and its many variants, Roberta, Albert, etc. These typically use just the transformer encoder stack. They are pre-trained using objectives like masked language modeling, predicting randomly hidden words in a sentence, and are primarily designed for natural language understanding, NLU, tasks, classification, entity recognition, question answering. Second, you have decoder-only models. The most well-known examples here are the GPT series, GPT, GPT-2, GPT-3, GPT-4. These use just the transformer decoder stack, usually pre-trained on a simple predict the next word objective over vast amounts of text. They excel at language modeling and sequence generation and are known for their impressive few-shot or even zero-shot learning capabilities, performing new tasks with very few or no examples, just from a prompt. And third, you have encoder-decoder models, which use the full original architecture. Examples include BART, T5, and the original transformer itself when used for translation. These are pre-trained with more complex objectives that often involve corrupting the input and teaching the model to reconstruct the original. They are versatile, capable of both understanding and generation tasks, and often perform very well on sequence-to-sequence problems like summarization or translation.
Got it. Encoder for understanding, decoder for generation, and encoder-decoder for seek to sec. Makes sense. And finally, looking at the broader landscape today, where can we actually see transformers at work? It feels like they permeated almost every area of AI.
They truly have. It's quite remarkable how universal the architecture is proving to be. Obviously, they started in natural language processing, and they still dominate there for machine translation, language modeling, text classification, named entity recognition, question answering, summarization, you name it. But then they made huge waves in computer vision. Models like the Vision Transformer, VIT, and Swin Transformer showed they could achieve state-of-the-art results on image classification, object detection, segmentation, and even image generation, often outperforming specialized CNNs. They're now used in video processing, too. We also see them heavily used in audio applications. Speech recognition models increasingly use transformer or conformer, transformer plus convolution architectures. Speech synthesis, text-to-speech, and even music generation models often leverage transformers. And maybe most excitingly, they are powering multimodal applications where models process and relate information from different types of data simultaneously. Think visual answering questions about an image, text image generation, like DALL-E or Stable Diffusion, image captioning, and even speech-to-text translation directly. Its ability to handle diverse sequence types makes it incredibly powerful for fusing modalities. It really has become a kind of universal computational engine for AI.
Wow, just an incredible journey. From that single, bold, groundbreaking paper back in 2017 that essentially declared attention is all you need,
Yeah.
to this absolutely sprawling ecosystem of efficient X-formers, architectural refinements, the pre-training revolution, and now applications tackling everything from language to vision to audio and beyond.
Hmm.
It's undeniable that the transformer has fundamentally shifted the entire landscape of artificial intelligence.
Indeed, it's quite a story. The journey from that initial elegant conceptualization through the very practical engineering challenges of making it scale to long sequences, and then the ongoing exploration of all these architectural nuances, it really underscores just how dynamic and inventive this field is, constant evolution.
Yeah, this deep dive really reveals how a powerful core idea, attention, when faced with real-world practical challenges like computational complexity, can just spur this cascade of incredible innovation. But it also raises a fascinating question, maybe something for you, our listener, to chew on. If the Transformer's original breakthrough success really stemmed from its unique ability to model these global dependencies across the entire input sequence via full attention, and yet, as we've seen, many of these successful efficient transformer variants demonstrate that full all-pairs attention often isn't strictly necessary. They achieve great results with sparse, approximate, or localized attention. What does this tell us about the future, about how AI models will learn to pay attention, and perhaps an even smarter, more selective, maybe even more context-dependent, and dare I say human-like way going forward? Something to think about.